Thanks, John, for the introduction. As John said, I'm the gas networks lead at NEL. Today, I'll discuss the impact of uncertainty in industrial flow measurement. This is a topic that is important to us, being the holder of a number of national flow standards. It's important that we quantify the uncertainty of these facilities to provide confidence to our customers. So this webinar will essentially go over the basics of uncertainty and why it's important to us. So first of all, I'll cover basic uncertainty theory, a bit about the terms that are commonly used in uncertainty theory, why they're important, and that will lead in nicely to the second section, which will look at the cost of errors, and this essentially emphasises why uncertainty analysis is important and the implications of not having the required uncertainty for various measurements. The next section we'll look at is types of uncertainty. So how do we determine uncertainty for various parameters? And that really is dependent on the information we have at hand. That will lead nicely into, again, is the uncertainty calculation stages. So we have a number of facilities and uncertainty budgets for our facility. In this section, will outline how we go about constructing a budget for a facility. And then again, that will lead nicely into a few practical examples. So we will look at how do we evaluate uncertainty for a final output parameter that we want to. So we can start in the first section. So if we go into basic uncertainty theory, so the first thing to realise is when you make a measurement, it's only an estimate of the true value, and it does not give the true value itself, and the true value itself is unknown. So if you think about use of a stopwatch, scales in your kitchen, or even a flow meter, what that instrument is trying to do is estimate what the true value is, and it hopefully will be somewhere close to the true value, but it won't be the true value itself. So that then leads us into uncertainty. In terms of the definition of uncertainty, it can be defined as an interval either side of the measurement result which we can expect the true value to lie with a given confidence. So in the image here, we've got our blue dot, which is our indicated value from our device, whether that be a flow meter, a stopwatch, scales, and we have our uncertainty bands either side, which are essentially saying our indicated value is here, but the true value may lie within these bands. And you'll quote a confidence level with that. And as you can see here, the true value does lie within these bands stated. The confidence level, that can be defined as the likelihood that a real value of a measurement will lie within a specified interval. The larger the interval, the higher confidence that a true value will lie within it. So here in this image, we've got the white section. If we expand our interval to include the blue section, we'll have a greater confidence that the true value will lie within the whole area as opposed to just the white area. And this makes sense. So when you state a result, there's three things you must state. You must state the measured value, so that is the output. The output, so this is whether it be from your scale, stopwatch, your flow meter, the associated uncertainty alongside this, as well as the confidence level. So as it says here, so the result of a flow measurement may be stated as 3.5 plus or minus 0.2 litres per second at a 95% confidence level. So what does this mean in practice? Your measurement is 3.5, but based on the uncertainty, there's a 95% chance that the true value will lie between 3.3 and 3.7. Error is another term that's commonly used, and this is the difference between the true value and the measured result. Because we don't know the true value, the error will be unknown. You do see error values stated from time to time, and where this is when you're comparing a device under test to a very accurate reference instrument that is very close to the true value. So you're comparing a result to a value that is very close to the true value, and at times you can see error values stated in that sense. Accuracy is another term that's used when dealing with uncertainty, and this is defined as the closeness of agreement between the result and the true value. You can have an accurate measurement with a large uncertainty, so in a sense you can almost strike lucky with a particular measurement and be close to the true value. But importantly, you cannot attach a value to accuracy. You can describe something as being highly accurate, very accurate, or compare two instruments and say this instrument is more accurate than the other instrument. But when you start talking about values, that is an uncertainty, and you need to quote the appropriate confidence level with it. And as it says here, this accuracy is a qualitative term and not a quantitative term. Repeatability, that's another term that's used. So this is the closeness of agreement between successive measurements under the same conditions at the same time. So for instance, again, another example is weigh scales. You could continually measure the same mass over and over again at the same conditions. Or you can set up flowing conditions in a laboratory and repeatedly take flow measurements using the flow meter and determine the repeatability. There's various methods to determine the repeatability, calculation methods. So if you do calculate repeatability, it's important to state the calculation method you've used. So if you have an accurate instrument, if you've got good accuracy, it ultimately means you've got good repeatability, because to be accurate, you need to be consistently or be close to the true value consistently. So to be consistently close to the true value, you need to have a repeatable instrument. If you have poor repeatability, you ultimately have poor accuracy. In a sense, you may strike lucky and be close to the true value with a measurement, but the poor repeatability of the instrument means you'll not always be close to the true value. And then the final point in the bottom left is good repeatability does not necessarily mean you'll have good accuracy. You could have a lot of measurements gathered around the same point, but they may not be close to the true value. Bias, this is another term commonly used, and this is when every measurement is affected in the same way. So this could be, again, a flow meter which over or under reads by the same amount each time. Again, weigh scales, over or under reading, and things such as that. You can correct for bias, but you need to consider the uncertainty in your correction. So next will be the cost of errors, to emphasise why care about uncertainty and why it's important in an industrial sense. So in 2019, there were an average of 81 billion barrels of oil produced per day in the world at a total cost of 5.19 billion. If you assume an uncertainty of 0.25%, this leads to a financial exposure of £13 million or dollars per day. And this shows essentially why uncertainty in this sense is important. It's important that people have confidence in what they can pay for, as well as governments, to ensure that they're getting the appropriate tax revenues. So low uncertainty flow measurement in this case is very important. A more practical example, if you look at petrol stations and refilling a car. So if there's a 2% uncertainty on the flow meter at the petrol station and you have a 50-litre tank, your uncertainty in filling the tank would be 50 plus or minus 1 litre at a 95% confidence level. And if we consider £1.45 per litre, and consider it financially. So the cost of filling your tank would be £72.50 plus or minus £1.45 at a 95% confidence level. And if we take it a step further and assume that you fill your car once per week, over the year you can be exposed to £75.40, either you, the consumer, or the petrol station itself. And this is only with a 2% uncertainty. It is achievable, but you don't want to have 5-10% uncertainty on things like that, because that can really lead to exposures for the consumer. So the next bit we'll talk about the types of uncertainty. I've quoted a few uncertainties and a number of examples, and in this section will really help us understand where we get the uncertainty values from, and then ultimately the final two sections will allow us to do some calculations of our own and understand where these values come from. So in terms of the categories, they can be broadly defined into type A or type B in uncertainty analysis. So type A is using real data, so it's using statistical data and generating an uncertainty value via that data. Type B is generally non-statistical methods, so it may be from a manufacturer specification sheet, so there may be manufacturing tolerances. You may have a calibration certificate where an uncertainty is quoted on it, or it may be just from judgment itself. But first of all, we will look at type A uncertainties. So type A analysis, so generally analysis of repeat measurements. When we repeat a measurement, it reduces the chance of errors, but repeats never agree. So subsequently, how do we decide which values to use, and what does the variation tell us? So best estimate of a true value. If we want to get the best estimate of a true value and we have a number of points, the best estimate would be the average of all these points. But if we want to go a step further and determine how spread out the values are, we could use the range. So you would subtract the lowest value from the highest value. But what this doesn't do is it doesn't characterize what's going on in the middle, and it ignores it, in this case, 8 of the 10 data points. So standard deviation is a measure of how essentially spread out the values are, and we can use an example to calculate a standard deviation. So if we have 10 readings for a flow of oil, shown below, we've got various readings between 73.1 and 73.9. Our first step in calculating the standard deviation is calculating the average of each of those points. And the average for each of those 10 points is 73.52. The next step is subtracting the average value from each of the 10 flow values, and this gives us a difference, 10 differences. We then square each of those values. So we have 10 squared values of the differences. And then we subsequently sum each of those 10 values together. We then take an average of those 10 values, but in this instance we divide by 9 as opposed to 10 to get an answer of 0.064, and I'll go on to explain on the next slide why that is. And then finally, we take the square root of that value in the previous slide to give us a standard deviation of 0.253. So based on the data we have calculated a standard deviation of 0.253, and essentially the 5 steps have evaluated the equation on the bottom left. So we have an x bar, and we've set that as our average, and for each of the 10 values for xi, we've calculated the difference, we've squared the difference, we've added the 10 differences together, we've divided by n minus 1. So the reason we have divided by n minus 1 as opposed to n, if you divide by n, you're only calculating the standard deviation of that sample of 10. But what we are trying to do with our standard deviation is we are trying to characterize what the spread would be in an infinite number of data points. And to do this, we divide by n minus 1. This actually increases the standard deviation slightly. So it accounts for the fact that we don't have the full population of data available to us and errs on the side of caution and increases the standard deviation slightly. So standard deviation, we've got 10 data points, but if we began to gather more data points, what you generally see for most things in nature and life, so if you think about people's weight, people's height, various other things, data tends to cluster in distinct patterns. And as you gather more data, you can see a pattern starting to emerge. So you get this characteristic bell-shaped or Gaussian or normal distribution curve where you can see that most points are centered around the average, and as you get to the extremes, the frequency of the readings decreases. So what does this tell us? So the standard uncertainty, or small u, is equivalent to the standard deviation. So the likelihood of finding the true value in this interval is 68% or 68.27% to be more accurate. 68%, this comes from a mathematical derivation from the cumulative distribution function, but I wouldn't concern yourself necessarily why it ends up at 68, but the previous calculation of 0.253 using the data set we had, this essentially characterizes where if we had a full sample, an infinite sample of flow values, approximately 68% of the values would fall between 73.52 minus 0.253 up to 73.52 plus 0.253. If the values were more spread out in our sample of 10 flow rates, you would essentially see a flattening of the curve. It would be flatter at a smaller peak, and the standard deviation would be larger. So essentially, the standard deviation for a normal distribution characterizes how tall or short or wide the shape of this normal distribution curve. And that makes sense. If you've got a large standard deviation, the values are more spread out, your curve is going to be flatter. Whereas if all the values are centered around, are closely grouped around the average, you're going to have a taller peak where more of the values, you're going to have a lower standard deviation and more of the values will be close to this peak. So expanded uncertainty is a term that's used as opposed to standard, and this is the uncertainty at a difference confidence level. So our standard uncertainty is at a 68% confidence level, so we have 68% confidence that the true value will lie within plus or minus 1 standard deviation. But if we want to have more confidence in the fact that the true value will lie within the intervals, you need to multiply the standard deviation of 0.253 by 1.96, and this increases our confidence level to 95%. And this is illustrated here. So we've got our 68% confidence level at a coverage factor of 1. If we want to increase the confidence that the true value will lie within here, we essentially multiply by the appropriate coverage factor, and that widens the uncertainty bands, and you can see it's collecting more data. There's more data within the two coloured lines, and essentially it's increasing our confidence that the true value will be within there. So we've talked about type A and generally around statistical analysis of a number of points, getting our standard deviation, and then subsequently our standard uncertainty based on that. Sometimes we don't have a wealth of data available to us, and this is actually quite common. So this is where type B comes in. So what do we do? So as it says here, not all uncertainty comes from type A analysis, and it's often that you need to assess uncertainty from other sources. So that may be using your own judgment. You might know that the true value will lie between two values, and you need to use your own judgment. There may be manufacturer's data, so they may quote that something is manufactured to a given tolerance, so it will be between two values. You may have an item calibrated somewhere else, so a reference temperature or pressure instrumentation that have been calibrated somewhere else, and it's come in a certificate, and it said the uncertainty is X at a confidence level of Y. And you're essentially just taking the uncertainty information that you have been given and applying it. As it says here, expanded uncertainty from the sources above is usually stated at a 95% confidence level. So if you use the coverage factor K as a divisor, you can convert back to a standard uncertainty. Yeah, and this is essentially just the reverse process of what we did before with increasing the confidence level. If you want to take it back to a standard uncertainty, you know what your coverage factor or confidence level is, and you divide by the appropriate factor. And this is shown here for a normal distribution. If you're assuming a normal distribution, to convert from expanded to standard uncertainty, you need to know the distribution. If you know generally it's from repeat measurements, but you don't have the repeat measurements, you tend to use a normal distribution. And it may be quoted at 95%, so you may have a calibration certificate stating that the calibration uncertainty is X at a confidence level of 95%. So to get it back to a standard uncertainty, you would divide by 1.96. Yep, so you may get a coverage factor, so K, given in a calibration certificate. You may get a confidence level, and subsequently you can look up K from a lookup table. There's plenty available online, and even Excel has a function for the various lookup values. We've only spoke about normal distributions so far, but there are cases where the value lies somewhere between two limits with an equal probability. So in the case of a normal distribution, there's an increasing likelihood as you go towards the average that the true value will lie there. However, there are examples, as it says here, in instrument resolution, acceptance criteria, so manufacturing tolerances, where you can't assume that the likelihood increases as it does with a normal distribution the closer you are to the measured values. So in this case, to get a standard uncertainty, it would be 0.5 multiplied by the difference between the two limits over root 3, and that would calculate a standard uncertainty in that sense. So an example of this could be a flow meter itself. So if you look at a flow meter which reads 35, so if you look at resolution uncertainty, really that value, if the value the meter was sensing was between 34.5 and 35.5, it will read 35 irrespective of what the meter is actually sensing. So there is a resolution uncertainty there. So to get the standard uncertainty, we would apply the equation. So it's 0.5 multiplied by the difference in limits, the limit 1 minus limit 2, so that's 35.5 minus 34.5, divided by root 3, and that gives a standard uncertainty of 0.29. So there can be instances where you would want to reduce the resolution uncertainty, and the obvious answer here is increase the resolution of your meter. or the readout from the meter. And this essentially would decrease your uncertainty in the resolution. So instead of being anywhere between 34.5 and 35.5, the value being sensed by the meter can be anywhere between 35.05 and 34.95. And by doing this essentially reduces our uncertainty by a factor of 10. So this just illustrates that not everything is normal distribution, and you have to consider how you'd expect the data to cluster and what the probability is for various uncertainties. So now we can begin to look at the calculation stages involved in developing an uncertainty calculation, and this is something we do often with our various facilities, and I'll go through each stage that we go through. So first of all, is identify uncertainty sources. So if we have, in a sense, a flow rate, but it could be an average temperature or an average pressure or density, you need to identify all of the uncertainty sources that feed into that. So first of all, if you are using an equation to calculate any parameter, you need to look at all of the uncertainties in each parameter of the equation. Are you taking repeat measurements of that? So will there be an uncertainty in the mean? And this is by no means easy. Identifying uncertainty sources, it doesn't only require, well, in a sense, it doesn't require any knowledge of uncertainty. It requires more of a knowledge of the process itself to identify the uncertainty sources. So you could be very experienced in uncertainty analysis of various things, but if you don't understand the process, physical, chemical process, identifying the uncertainty sources is difficult. So it does really rely on someone having knowledge of the process. The next stage is estimate the magnitude of each uncertainty. We went through the types of analysis. So that again, this could be analysis of repeat measurements. So it could be more along the lines of a type A analysis to get yourself a standard uncertainty. You may not have information available. You may know it's an uncertainty source, but have no information available. So you may need to use your judgment, in a sense, to estimate an uncertainty. You may have, as I said before, calibration certificates for instruments that have been calibrated externally. Or you may have manufacturing tolerances where you know that a piece of pipe work or a diameter of a pipe has been manufactured to a tolerance, and you know it lies, or you have an inkling that it lies between two levels, or it's been quoted. From there, you would convert to standard values. Generally, if you're doing type A analysis, you've calculated your standard uncertainty in the first place, but for type B analysis, where it may be a rectangular distribution and you may need to divide by half of the difference in the limits divided by √3, you may be quoted at a coverage factor of 2. You may be quoted at a confidence level of 95% for a normal distribution. And you need to use that information to convert from an expanded uncertainty back to a standard uncertainty for these parameters. The next stage is calculating the sensitivity coefficient, and this is the sensitivity coefficient is essentially looking at how sensitive your output parameter is to the uncertainty parameter you're considering. So there are various methods for this. The first is if you have an equation to calculate something, you could partially differentiate the output parameter with respect to the input parameter. But this can get a bit complex with more complex equations, and normally a numerical method used where you can do a small increment, typically a standard uncertainty, increase to the input parameter and see the change it has to the output parameter. And similarly, you can decrement the input parameter and see what change it has to the output parameter, and then you can calculate a sensitivity coefficient. You then convert your standard uncertainty to an output value, and this is simply you multiply the standard uncertainty by the calculated sensitivity coefficient. Stage 6 is something we'll touch on at the end, and this is estimating a degree of correlation. And this is around sometimes you may have measurements that are not necessarily independent of one another. You may have two temperature measurements in a process, and both of these temperature probes have been calibrated against the same reference. And this needs to be considered because if the temperature is out one way with the calibration, it's going to be out the same or likely to be out the same for both parameters here, and this needs to be considered, and it's quite important for more complex processes. Depending on whether it's correlated or uncorrelated, most of the examples here will just be on uncorrelated methods. You combine using the appropriate method, and the method used for uncorrelated is the root sum squared method. Again, we'll go into this in a few examples. And then finally, you express at the appropriate confidence level. So everything has been converted to a standard uncertainty. So once you've combined using the appropriate method, you will have your standard uncertainty. So if you want to express your final uncertainty value at a confidence level of 95% or 99%, you need to use the appropriate multiplication factor to get back to that. So we can now look at a few examples. I appreciate it might have been a bit heavy in terms of technical material in the last few slides, but the purpose of these is just to tie everything together and understand how everything feeds into an uncertainty calculation to get as a final output for uncertainty. So if you take the example of an orifice plate, so a differential pressure device, flow measurement device to calculate mass flow rate. So in the box below, we've got our mass flow rate Q, and we have an equation derived that calculates the mass flow rate, and we have a number of parameters in this equation. So we have the discharge coefficient, which accounts for frictional effects, beta, which is the ratio of the orifice diameter to the pipe diameter, expansibility factor epsilon, the pressure differential, which is calculated from the U-tube manometer, difference in height, and also the density of the fluid as well. So we have a number of parameters. All of these will have uncertainties, and we want to calculate what the uncertainty is in the mass flow rate. So how would you do this? So if we think about the steps we spoke about previously, we've got our values for each of these. These aren't their uncertainty values, these are the absolute values for them. So we've got our value for discharge coefficient, expansibility factor, both the pipe and orifice diameter, the pressure drop, and the density. So you can calculate the flow rate. So the flow rate perfectly works out at 100 kilograms per second based on these values. So in a sense, identifying all the parameters, identifying the uncertainty in all the parameters is relatively simple here. You've got your equation, you know what your parameters are, and we can take it from there. The next step is estimating what the magnitude is for the uncertainty. So discharge coefficient and the expansibility factor. So these have been quoted and determined as a percentage. So the expanded uncertainty of the discharge coefficient is 0.5%. We can convert that back to a relative, an absolute uncertainty as opposed to a relative or percentage uncertainty by dividing by 0.6. Similarly, for the expansibility factor as well, we can convert from a percentage uncertainty, divide by 100, and the 0.977 as well, or multiply by 0.977 as well, and that gives us our absolute uncertainty expanded of 0.0027. For the pipe diameter and orifice diameter, these are already given in absolute as opposed to relative uncertainties. So we have our uncertainty in the pipe diameter and orifice diameter. This may again be from manufacturing sheets or wherever we purchase the pipes from. Pressure drop and density. These boxes have been highlighted in red because pressure drop, so we used in the previous slide, we showed a YouTube manometer. This pressure drop will be determined by the height difference as well as the fluid density in the U-bend. So there essentially will need to be a separate calculation in determining the uncertainty of 100 pascals in the pressure drop, and it's just to illustrate that you may have uncertainty calculations that will feed into subsequent uncertainty calculations, and each of the determination of the height difference in the YouTube manometer as well as the density will have an uncertainty associated by it. And similarly, the density as well. The density will be determined by an appropriate equation of state. There will be measurements of temperature and pressure as well. So these need to be considered and applied when calculating the total uncertainty and the density as well. So we've now got our expanded uncertainty values. You know, it may be, as I said, from different methods. You may have the first two or the first one discharge coefficient quoted in a calibration sheet. You may have manufacturing tolerances for the pipe diameters. You may have calculated the pressure drop and density uncertainty separately. But now we take it to the next phase, and stage 3 is getting it in standard uncertainty. So what we need to consider now is our distributions. So for the discharge coefficient, expansibility factor, pressure drop and density, we're assuming that these are normally distributed around the mean at a coverage factor of 2. So based on this, we would divide by 2 to get our standard uncertainty. For the pipe diameters, as I said, if these are from manufacturing specifications and the manufacturer quotes tolerance levels, so it's essentially saying the value can be 0.001 above, 0.001 above, or 0.001 below 0.5 for the pipe diameter. Because it is a tolerance level, you err on the side of caution and say it can be anywhere within these tolerance levels. And by doing that, you assume a rectangular distribution. 1.73 is the same as root 3. So if you divide by that, that gives you a standard uncertainty. And that's conservative because you're dividing by a smaller value, and subsequently your standard uncertainty will be greater. And the reason this is greater is it's because you've got less of a certainty in where it will lie within the distribution. It's a rectangular distribution. For normal distributions, you've got a greater certainty that it will lie closer to the mean as opposed to the extremes. From there, now we've got our standard uncertainties, you would get the sensitivity coefficient. Again, as I explained before, you can partially differentiate, so you would have dq by dc, partially differentiate the equation, and enter the values for the other parameters. However, this can be difficult and get more complex. So for example, D2, if you want to find out the sensitivity coefficient for D2 is within here. It's within the D2 squared, and it's also within the beta to the power of 4. So differentiating that can be complex. So what you tend to do is calculate Q, you use all the same values as you have for every parameter apart from D2, where you would make a small increment increase of 0.3 plus the standard uncertainty of 5.78 times 10 to the minus 6, and you would see what your Q value is. And then you would also decrement the value in a sense that you would use 0.3 minus that value and calculate what Q is. And then you can get what the change is in Q with the subsequent change in D2. And that gives you your sensitivity coefficient. And what the purpose of this is, you're essentially converting it to output units. You're looking at how sensitive the output parameter of calculated flow is compared to the parameter in the equation. So you then multiply the column U by the column C to get the UC term for each of the parameters. Because we are assuming the parameters are uncorrelated in this particular example, the method for combining it is the root sum squared method, and this squares each of the UC terms and then sums them. It may be common to think that you can just add them together, so add all of the UC terms together in the purple column. But what this does is it doesn't take into account the fact that you can have things at different places in the distribution. Not everything is going to be out by its maximum or top or low end of the uncertainty distribution. So this root sum squared method takes into account that essentially and calculates a more practical value based on uncorrelated uncertainties. So in the column at the far right, we've got our UC squared terms. We then sum them. We take the square root of the sum. So that takes 0.0711 back to 0.267. The sensitivity coefficient is 1 because we're already in the appropriate units for flow using the sensitivity coefficients. And then we can use any coverage factor we want, just depends what we want to quote the uncertainty as, multiply by 2, and that gives us a calculated flow of 100 kilograms per second with an uncertainty of 0.533 at a coverage factor of 2. So the coverage factor of 2 is just over 95% confidence. So our result is what the result says based on the uncertainty analysis is that we have around just over 95% confidence that the value will lie between, the true value will lie between 100 minus 0.533 all the way up to 100 plus 0.533. Another example is if you look at tank volume. So if you take the volume of a storage tank, it's a relatively simple equation, pi d squared h over 4. There is a little bit of additional complexity to it in the sense that you need to calculate a standard volume based on a temperature of 15 degrees. You may be measuring the tank in winter or summer, and temperature fluctuations mean that the tank can change size. So if you use a coefficient of thermal expansion, you can standardize the temperature, the volume of the tank to a temperature of 15 degrees C by recognizing the temperature at which you took your measurements of height and diameter. So if we look at an uncertainty budget for this, similar to the previous one, we've got recognise here now that we didn't have this before, but we have got 3 different sources that feed into the uncertainty of our diameter. So we've got the calibration uncertainty, determination, so the method of determining diameter, and also the drift of the diameter over time. So it's important to recognise that you can have more than one uncertainty source for one parameter in the equation. And similarly, this is the same for the height. And then you've got your temperature and cubical expansion as well. Again, similar method, we've got our expanded uncertainties. You divide by the appropriate coverage factor, depending on whether it's normally or rectangularly distributed. These are the 2 common ones we almost always see. Get the appropriate sensitivity coefficient in the red column, multiply the standard uncertainty by the sensitivity coefficient, and get our UC squared term on the right hand side. We sum each of those terms, take the square root of 2.541, and that gives us 1.594, the uncertainty. If we want to quote a coverage factor of 2, you need to multiply that by 2, leaving an uncertainty in the volume of 3.188. So it can be common when we do budgets for facilities or prospective facilities or anything that the overall uncertainty we calculate is too high. We've made a concept design of something and it's too high, or perhaps an auditor comes in and we need to demonstrate that the uncertainty is lower for a particular process. So the first thing you do here, or provided that it's cost effective, is you look at your largest UC squared term, because that's having the largest contribution to your uncertainty. So if you can make a reduction in that, you're going to make a reduction to your overall uncertainty. So in this situation, the calibration uncertainty for the diameter is the largest uncertainty source, so it's the largest contributor. So if we can reduce that, and in this case half it, it will reduce the uncertainty from 3.188 down to 2.720. This can be an iterative process, so now that we see that the uncertainty in the height calibration is our largest source of uncertainty, so we can now look at decreasing that. Again, to show if we have that, we can reduce our uncertainty further. Now that leaves the method of determination of the diameter as the largest uncertainty source. And again, just to illustrate, if we want to reduce that, we can reduce that further and take the uncertainty down further. So this is just to illustrate that if your uncertainty is too high, you look at the largest sources first. If they can practically be reduced, try and reduce them first, as it will have the largest impact in reducing your overall uncertainty for the facility or for whatever process you're interested in. Something I've not touched on a lot is correlation. In our examples, I've only considered uncorrelated measurements. So measurements, it says here, are independent. They may be at different parts of the uncertainty range, and as it shows here, we've got two flow meters, and we're taking measurements. In the first case, our flow meter U1 or the uncertainty is overreading, so our true value is actually below what's been read. And then in the other case, our meter is underreading. So this is the reason or the root of where the root sum squared method comes from, because if you have lots of values feeding into one another, it's very unlikely that they're all going to be overreading or they're all going to be underreading if they are uncorrelated. So the uncertainty of the combined flow can be used, the root sum square method can be used, so you would have the uncertainty in 1 squared plus the root uncertainty in 2 squared, and you can take the square root of that. And that takes credit, as I said. The thing to emphasize here is this takes credit for the fact that if you have a large number of independent measurements, the likelihood of having them all on the same side of the uncertainty bands is small. But if we now look at correlated measurements, so if both of the measurements are made by 1 meter, if the meter underreads, for one reading it will underread for them all. So it's going to be at the same side of the distribution for both. So we can't take credit for the fact that these measurements aren't independent. They are correlated and dependent on one another, and if the meter is out one way, it's going to be out the same way for both. So you typically, the simplistic case is adding the uncertainty terms together simply, as opposed to squaring each uncertainty term, adding them together and taking the square root. And we can look at this if we go back to our volume example, we can take this as an example. So again, this is our tank volume. If we assume that the instrument used to measure the diameter and the instrument to measure the height was calibrated against the same reference, if the reference meter is out, if the thing being used to calibrate the height and diameter instruments is out one way or the other, it's likely that, or it's almost certain that the uncertainty and calibration for diameter and height are correlated, and they're going to be out the same way. So using the root sum square method isn't appropriate in this case. And in a sense, what we do, as I described in the previous slide, you can simplistically add the values together, the UC terms together. So you would have 0.955 plus 0.905, and then you would square them. And then you would continue with the rest of your process, because the rest of your values you're still determining as uncorrelated. And you get down to your UC squared, the sum of your UC squared of 4.277. You take the square root of that, get your appropriate coverage factor, and that leaves an expanded uncertainty of 4.136, when it was previously 3.188 when you assumed it was uncorrelated. So this is just a small example to really consider correlation. In some cases, in a lot of cases, it does increase your uncertainty. Particularly, the most common case I see is when you're using multiple instruments that have been calibrated against the same reference, and this needs to be considered because the calibration uncertainty will be out the same way, and you can't take credit for that and root sum square everything together. So just a summary on handling uncertainty calculations. First of all, always convert to a standard uncertainty before performing calculations. So determine your appropriate distribution, see what the coverage factor or confidence level is. Ensure that your units are all identical. In our case, for example, in the orifice plate example, everything was in SI units. So everything was in the correct units. Be conservative, and in a sense, always round up. And the last point goes back to understanding not only uncertainty, but understanding the process itself and whether what you have calculated or estimated feels right based on your knowledge of the process. So a bit on further reading. This presentation essentially only covers a small section of the guide to the expression of uncertainty measurement, and this really goes into quite a bit more detail in terms of type A uncertainty analysis, correlation, and things like that. This was prepared and published by a consortium of international standards bodies, and it is recognised as providing standard methods around the world on uncertainty analysis. And just to summarise, measurement is meaningless. In a sense, it's meaningless without a statement on uncertainty and associated confidence level. What your final uncertainty is it's describing how good or your quality of your measurement. If you've got a low uncertainty and you've demonstrated that, it's telling you've got a high quality measurement, and in some instances you do need to demonstrate that you have a high quality measurement. Assessment of uncertainty can be time consuming and requires careful thought. No uncertainty analysis is ever perfect. It's very difficult to identify every source of uncertainty, particularly in complex facilities and processes. And it does take time. It takes time to understand the process, the uncertainty calculation, etc. But if it's done right, it will save time and money in the long term. And going back to that point about no uncertainty analysis being perfect, this is the reason why measurement institutes across the world do intercomparison studies where they will take some form of transfer standard, and they will move it from different labs across the world. So if various labs are claiming a certain uncertainty, the results for the transfer package should match up. If every uncertainty analysis ever carried out was perfect and we had all the information, there would never be a need for intercomparison study. But doing things like intercomparison studies, a further method of confirming the uncertainty budgets that have been predicted. That's me. I think I'm happy to take any questions. I think we've got a bit of time, a few minutes, so I can take a few questions. Pass you over to John. Right. But thanks everyone for listening.
Thanks for that, Dale. Yeah, we've got quite a few questions come in. I'll kick off first of all. Uncertainty budgets, right? What are they? Why do I need them? And how often should I do them? This is quite this one rings home with me because we've over the years we've had a lot of companies come to us and ask us to do uncertainty budgets for them, or to train their own people to be able to do their uncertainty budgets. So, Dale, what's your thoughts on that?
Yeah, uncertainty budgets are an attempt to quantify all the uncertainty sources in a particular process. We can take an example of a flow facility. So we have many flow facilities that will try and estimate the uncertainty for the facility, and then subsequently, if we test a meter in it, what the uncertainty is for the ultimate test meter. The budget takes every uncertainty. So if we use a gravimetric primary standard, it will be of the weighbridge, any other measurements that are taken in the process. If we use more of a nozzle array, use sonic nozzles as a reference standard in a sense, we will have temperature, pressure measurements, density measurements, viscosity, and it will really summarize all this information, take the uncertainties for each of these and do a calculation similar to the examples, but obviously in a bit more detail to give an overall uncertainty in the facility that we can present. And this is important because it will give any customer who wants to assess the performance of the meter confidence that we have a low enough uncertainty that we'll be able to assess their meter based on their desired final uncertainty or accuracy of the meter.
Yeah. Okay. Right. We're fast running out of time here, so we do have quite a few questions. So I think, as we said earlier, any of the questions we don't get to, we'll get back to you on. But I think very quickly, and we'll probably get time for one more. If you have a liquid metering system with multiple parallel meter runs and a common shared prover, how do you calculate the total system uncertainty? Some of the individual meter run uncertainties or the square root of the squared sums? I don't know if that's a question you can answer in the next
If you
minute,
have a
Dale.
if you have not, I'm looking at it just now. If you have a liquid metering system, that is
Yeah,
something
no
I can
matter.
look at.
Yeah, we'll come. We'll we'll
I've
we'll,
got
we'll
the
reply
name.
to that one
Yeah,
after. Yeah, because
yep,
we're running
absolutely.
out of time. Okay, listen, folks. Sorry about that. We've actually come to the end of this, but as I mentioned earlier, you will be sent a link with the recording for today's presentation. Keep in touch with us. Let us know if there's any webinars, any subjects you want us to do, or if you want us to run something this one again. You can contact me, or you can send any queries to info.uk@tufsud.com. Visit our website www.tufsud.com/UK. On behalf of myself and Dale, thanks for your time today and enjoy the rest of your day.